Well, for the second activity of today, we have the first hands-on session on BGP. There is some material that was developed in this last few months, and we will have Ali Alsabeh. He's the developer of this lab. He's a grad student at the University of South Carolina. I will start this session, and then I will let Ali continue. I want to give credit to these two grad students who developed these labs, Ali Alsabeh and Sharen Sharif. Ali is a first-year PhD student here at the College of Engineering. Sharen is a master's student at the University of South Carolina, also College of Engineering. And there is a set of labs, and again, all these labs are available. After the workshop will be available by logging to the portal, and there are several labs. But before discussing the lab, I want to briefly mention the history behind these labs. And I have to go back to December 2019 during the Technology Exchange Conference that was in New Orleans. And during the meeting, it was mentioned, it was clear that there was a need for some BGP training, hands-on training. For those who are not familiar with the Technology Exchange, this is a main technical event in the global RE community for scientists, researchers, engineers, operators, students, faculty, I would say. But in addition to that, at the universities, I'm not a network engineer, but I teach some classes in networks, and we teach BGP, and this is being taught at different levels. Professional certifications, I can mention some very popular one, CCNA, CCNP, all those cover BGP. Also, 2-year technical colleges, 4-year universities, and at grad school. Now, on my opinion, BGP is very complex as an educator, and I have another perspective, is the educator, because it just has so many features, and it's difficult to master BGP. Even after having read books and RFCs for the students and also for the instructors, it is difficult to master BGP without practicing it. I have 2 books here, very good books in computer networks. And on the left-hand side, the book by Kuros Ross. We use this, and when I was a student, I used this book as well. A very good overview, but there is a lack of hands-on in most of the training material. With that background, we decided to create a lab series for BGP, and this lab, or many of the labs are used at the University of South Carolina, USC, University of South Florida, University of Texas, and some others. With very good results. So we decided to put in place this lab series covering the most essential aspects of BGP. For example, what Eli and Hans were talking about, the ways that BGP route traffic, for example, autonomous system path attribute, or BGP local preference, or the MET attribute. There are some other labs that are a little bit more advanced, for example, multi-protocol BGP, route reflection. But the idea is to let a trainee start from 0, and then by the end of the 13 labs, and by the way, we continue developing new labs. Hopefully we will have about 20 labs on BGP within the next few months. Starting from 0, somebody should be able to be very proficient in BGP after completing these labs. The lab series include an overview, for example, objectives, roadmaps, Then a section 1 where the background information, the theory is covered, and then the step-by-step section 2 to section N. Some labs have more sections than others. So I will start by giving a flavor of how the lab looked like, and then Ali will continue and we'll do some labs, and we will be open for questions. And those who have access to the pods, they can access the pod and try this material. So the first one is introduction to Mininet, and the reason is we use Mininet to create the networks, the different autonomous systems. Within Mininet, we emulate different autonomous systems and create like an emulated internet. With Mininet, each node is an independent network namespace. That means each single node has virtual interfaces, like a router will have 2, 3, 4 interfaces. We'll have a routing table. If BGP is running, it will have a BGP routing, BGP table as well. And the nodes use the underlying protocol stack of the device. In this lab series, the device is a Linux machine, so all the nodes are running Linux. So on the right-hand side, we have how Mininet look like. On the left-hand side, we have the topology. And in this example, we have one router connecting 2 networks, 192.168.1.0 and 2.0. And the translation to Mininet is straightforward. Router R1 and the different switches, and the end devices H1 and H2. Now, the next question is what we use for as a router. And we decided to use FR routing. For those who are not familiar with FR routing, is an open source routing protocol stack. And at the bottom is the link. The source code is available. It provides similar routing capabilities to other vendors. That means protocols such as BGP, OSPF, RIP, etc. are all available with FRR. It runs natively on Linux. That's what we use for the labs, but also runs in other platforms. Ali, who is going to be doing the labs, for example, he's using in white boxes. We use in edge core switches. The configuration of an FR routing is similar also to other vendors. If you are familiar with a command line, for example, Cisco iOS, so it's a similar interface. And there is a way to also run the router through a configuration file, or configuring by using a file. Now there is a little bit of difference with at least with the protocols that I'm more familiar, in the sense that the different protocols are implemented as daemons, individual daemons. For example, we have BGPD, RIPD, OSPFD, and several others. And the network engineer, the person who is manipulating this router, will interact with these daemons using the command line interface. Finally, there is a service daemon, which is the core of FR routing, which is the process that controls the routing information base, the control plane. What are the routes that are placed in the routing table, or make the intercommunication between different protocols, for example, for routing advertisement. Zebra is the core of FR routing. So the way that we design these labs, we use Mininet. Mininet provides the network emulation. And then we use the routers, FR routing. The set of commands provided by FR routing are inherited and can be run using Mininet, running a real protocol stack. The lab number 2 is a simple lab. There are 2 autonomous systems. Those are shown on the right-hand side. And the intention is just to try FRR Mininet. There is a network 192.168.1.0, a remote network 2.0, and a network between those two. This is on the left-hand side, we have the terminal, the command line CLI for router R1. This is how FRR look like. At the very beginning, we're starting this process Zebra, which is the core. And then if I want to use a static routing, what I would do is I will start the static routing daemon. If I want to use BGP, I will start the BGP daemon or the OSPF daemon, etc. And then entering the shell. And this is the way to install a static route. So at this point, what I will do, rather than going through the slide, is I will switch to the virtual platform. And I will continue with this same example. And then I will hand out to Ali. So in the virtual platform, I will schedule a lab for myself. We're trying BGP lab series. Yesterday lab series are under network tools and protocols, and tomorrow will be SIG. I will test this lab number 2. There's a pod available here. And I will enter the lab. This is a very lightweight pod. It's not as complex, for example, as PREF Sonar, the one that we saw yesterday. PREF Sonar has 7 virtual machines. In this case, we only have 1 virtual machine. But inside that virtual machine, we emulate networks using Mininet. So lab number 2, I will follow the instructions. The password is password. And again, the section number 1 will give you the background, the theory behind this. Much of what Eli and Hans were talking, some things you will find here as well in more advanced labs. In this lab number 2 is how FR routing works, the architecture. Then the topology, this is the topology that we will use for lab number 2. I will come back to this. I already went through this first step. The second step I will open, and of course we can build our own topology, but these topologies are already built for us. In this case, I will go to topology lab number 2, which basically is the image of this network. The network number 1 is 192.168.1.0. The network 2 is 2.0, and there is a network between them, which is 1.2.0/30. Now, before, because there are the more advanced labs includes many more devices, routers, switches, and devices. And it's a little bit tedious to configure the individual IP addresses to the different interfaces. If a router has 2 interfaces, then we have to configure the two of them, subnet mask, IP address, etc. In order to avoid this first step, which is just configuring IP addresses, we can automate that. That's what the first few steps are about. I'm following lab number 2. And there is one script that will configure for us the IP addresses. We'll prepare and we'll speed up the whole lab. Okay, so all the different IP addresses were configured. In this case, H1, R1, R2, H2. That's all I have to do here. And then running the emulation. So we can, these are, again, different network namespaces. So H1 is a whole device. I can check the IP address 192.168.1.0. I can check also the router, and these two routers are FR routers. When we work with FR routers, we first start the daemon Zebra. In this first lab, I will only use the static routing. So I will start the static routing daemon. And then I will use the VTY shell, which is the command line interface. Again, and this is the process to run, to start the router. I can check, for example, show the running config, which is the configuration file. And we already have the first interface facing the network 1 with the IP address 11/24. That means the prefix length is 24 bits. The interface R1 ETH1, which is facing router R2 with the IP address 192.168.121/30. We can check the routing table. We have two directly connected networks. 1.0 is the one facing switch 1, and the network 1.2 facing the router 2. The output interface to reach those networks. And again, all this is explained in detail in the lab manuals. Now to configure for this first lab, I mean, this is just introducing you, we're introducing you FR routing. The lab will show how to start BGP, how to start OSPF. I will show a very simple example how to install a static route in FRR. I will use this, the command IP route. Of course, moving to config mode, IP route. I'm in router R1. I will install a static route so that router R1 is able to reach the network 192.168.2.0. The command IP route, first parameter, the remote network. The second parameter, the next hop. 192.168.1.2.2 is the IP address of router R2, the interface facing R1. Okay. If I check the routing table, I have a static route right now. The S stands for static. The second column is the remote network. Administrative distance and metric. And then what is the output interface to reach that network? I will send a packet to H2 from router R1, sending a packet to H2. And there is no connectivity. I have to also install a static route in router R2. So what I will do is I will follow the same commands that I follow in router R1. Starting Zebra. static daemon, VTY shell, config mode, the IP route. I am installing a static route in router R2 so that router R2 is able to reach the network 192.168.1.0. Next hop will be 192.168.1.2.1, and that is the IP address of router R1 facing router R2. Checking the routing table, I have a static route to 10/24. The next hop is 121, so hopefully we will have connectivity from router R2 to network 1. So we have connectivity. Again, so this is the way that we interact with FRR. It's very similar, as I mentioned before, very similar to other vendors' interface. Now, the lab number 3, that's lab number 2. I went, even though we didn't cover BGP yet, I wanted to show how FRR looks like. Now, lab number 3 is about BGP, and here is where we start discussing BGP, what Eli and Hans were talking about. So I will let Ali continue from here. Ali, can you share your screen?
Yeah, sure. Okay. Can you see my screen now?
Yes, we can see, Ali.
Okay, thank you for the introduction, Dr. Jorge. So what is BGP? So basically, the internet is like divided into a set of autonomous systems, and BGP is the protocol that is used to steer the traffic between these autonomous systems. As we can see here, we have two autonomous systems, 100 and 200. When the routers running BGP are within the autonomous systems, they are called iBGP neighbors. However, when you're pairing with another BGP speaker and different autonomous systems, these are called external BGP neighbors or eBGP. So the topology of lab 3 is as follows. It's kind of similar. It's similar to the previous lab, which has two autonomous systems, 100 and 200. And basically, instead of doing the static routing, we're gonna configure BGP. So, for example, on each router, we're gonna configure BGP neighbors so that BGP neighborhood is established, as well as we're gonna advertise the network so that both ends learn how to reach this network. So, as we said, how do we configure BGP? First, let's take as an example router R1. As we enable static routing, the first step here is to enable also BGP daemon. And let me show here. This is the BGP daemon. This should be enabled before configuring BGP routing. And then we enter the VTY/SH session. And then in order to configure BGP neighbor, we put the command neighbor and we specify the IP address. For example, here we have 192.168.12.2, which is basically refers to router R2. And we have to specify the autonomous system of the neighbor router, which is 200. So now, let's say that we have established BGP neighborhood between both routers. Still, each router does not know how to reach the other network. So, for example, router R2 does not know how to reach network 1, which is 192.168.1.0, because yet it's not advertised by the neighbor router. In order to do that, this simply can be done by the network command, and we advertise network 1 on router R1. And similarly, we do the same thing On router R2, we advertise the network 192.168.2.0. And basically, after establishing BGP neighbor and advertising the network, if you go to the router R2 and show the routing table of it, we can see here first, when we write the command show IP route, there are different codes. These refer to the protocol that's used or that was used in order to land the route. For example, O corresponds to OSPF, B corresponds to BGP, and so on. So here we see the entry 192.168.1.0 is inserted inside in the routing table of router R2 via BGP. And to reach this network, the next hop is 192.168.12.1, which basically corresponds to R1. Similarly, we have the BGP of router R2, which basically lists the networks that are learned via BGP only. And here we can see there are two networks, the local one, which is 2.0, and the one that's learned from router R1, which is 1.0, and the next hop. So this was for lab 3. We're gonna move now to configuring it shortly. Basically, I'm here in my reservation, the same step I followed as the lab 2. Created a reservation, and now I'm gonna log in into Mininet. And one more thing is that the content of the lab, you can see it here inside the content. You can download it and navigate through the lab. So what I'm gonna do here is I'm in this step, for example. Okay. So first launch Mininet and then navigate to the topology, which is lab 3. Here we have it. Then we click the run button. On router R1 first, as we mentioned, we have to enable the Zebra daemon, then the BGP, enter the VTY/SH session, and configure the terminal and the autonomous system of router R1 is 100. So here we can start establishing the BGP neighborhood, and our neighbor is 192.168.12.2. and the autonomous system of router R2 is 200. This command, as we mentioned, it establishes the BGP neighborhood in order to advertise the network so that it's inserted in the routing table of the peering router. We have to write the network command 192.168.1.0 and the subnet mask. And a BGP table, as we can see here, the first network is learned via BGP. This is the local one. Similarly, we follow the same steps. BGP on router R2, and the autonomous system of router R2 is 200. The neighbor of router R2 is router R1, which is 192.168.12.1.
Ali, do you want to show the topology? Because I think it's going to be good to show what exactly you are doing, because the topology that shows the different autonomous systems.
Okay. So here, as we can see here, we have autonomous system 100 and autonomous system 200. Basically, what I did here is that router R1, I established BGP neighbor with router R2 192.168.12.2, and I advertised the local network of router R1 192.168.1.0, and similarly, I'm gonna follow the same steps on router R2.
So if in that, so with the network command, your router R1 is advertising the network 192.168.1.0.
Exactly. Yes.
Okay.
192.168.12.1, and the remote autonomous system is to 100. And now we advertise network 192.168.2.0 on router R2. Now, if we show the routing table of router R2, as we can see here, oh, sorry, the network of here, the network 192.168.1.0 is learned by router R2. And similarly, if we see the routing table of router R2, we're going to see that the network, other network is also learned. So here it is. And similarly, show IP route. This is the network that's learned. Now, if we try to ping, we should have a successful connectivity. I'm gonna launch the terminal of route host H2, and I'm gonna try to ping host 2, and here we show a successful connectivity. Control C in order to stop the ping, and we have a 0 packet loss, which means a successful connectivity. So that's basically how do we configure BGP. That's a really simple BGP scenario where we establish the neighbor relationship, BGP neighbor relationship, and we advertise the networks. Now, moving to the other lab, which is configuring iBGP, eBGP sessions, and local preference admin. So what are BGP attributes? These are when a router basically advertises a BGP prefix across the internet, it includes a set of BGP attributes, which are used to select the best path when there are like multiple paths to the same destination. Local preference is one BGP attribute that's used by BGP in order to select the preferred path to an external autonomous system when there are multiple routes to this autonomous system. So for example, if a link has a higher local preference than another one, it's going to be preferred. And as seen in this figure, we have two autonomous systems. They are connected via two links, one from R1, R3, and one from R2, R3. So the local preference is configured on both links, and the one R2, R3 has a higher local preference. So whenever any packet wants to leave autonomous system 100 and reach autonomous system 200, it will always select this path, R2, R3, since it has a higher local preference. The med attribute, this is another BGP attribute that's kind of reverse of local preference. It basically indicates to external neighbors how to enter what is the preferred path to an autonomous system. So basically, before we've seen that router R1 and R2 are making the decision to reach autonomous system 200. Now, what if the autonomous system wants to tell other external autonomous system how to reach their network? Basically, they configure the med attribute, and contrary to the local preference attribute, the med with the lowest value is the one that's preferred. So the topology of this lab is as follows. We have two autonomous systems, the internet service provider and the campus. And as we see here, these autonomous systems are connected via two links. This is the primary link and this is the secondary link. And you can let's say that the primary link has a capacity of 100 gigabit and the secondary one has like 10 gigabit. Of course, we don't want to steer the traffic to the ISP or to the other end using the secondary link because it's gonna have a lower rate. So what we want to do here is that we want to configure BGP so that this primary link has a higher is the preferred one. Is the one that's favored when you move when the traffic is steered from autonomous system 100 to autonomous system 200. So in order to do that, first on the router R2, let's say that we want to configure the local preference for the primary link. So this can be done on router R2 because it's basically the one that's attached the end of the primary link, and So what's gonna happen is that first we're gonna establish a configure route map, and a route map is basically a series of statements that like permit or deny after checking if the route matches the policy. So here we're gonna create a route map. We're gonna call it primary N because it refers to the primary route, and the action is gonna be permit. Now we have to set the local preference of the route map that we created, and the primary link is going to have a value of 150. Now that we've created the route map and set the local preference, we need to assign it to the neighbor, which is basically router R1. We need to assign that the primary link has is attached to this route map, and this can be done using the neighbor command. And we put route map, and the route map that we've created, we called it primary N, and the N here, other N, is basically refers to the inbound traffic that's coming to the router. Now we've like created the route map and assigned the local preference for router R3. Similarly, we can copy the same steps on router R3 because we're gonna basically set the local preference for the secondary link. So we're gonna use router R3 and similarly follow the same step. However, here we're gonna assign it a lower local preference because we don't want to steer the traffic using this link. So that's why we assign a lower value. And then similarly, we assign it to the neighbor 13.1 and the secondary link. So now after we've established like the primary and the secondary link, and we established the local preference attribute, let's consider the BGP table of router R3. So basically, router R3 should use the primary link to steer network traffic for ISP, or the Autonomous System 100. And this can be seen here in the BGP table of router R3, where we have the next hop of the network 192.168.1.0 is basically 192.168.12.1, which is basically the primary link. And although the router R3 is directly connected to the internet service provider, it won't take this path. It will take the other one, and which is basically not the default behavior of BGP. So let's move to hands-on. So I've created the lab. I've already configured it so that we don't have to reiterate over the whole process again. So now this is our topology. This is the content of the lab. This is our topology. And what I'm gonna do is that I'm gonna set the primary link, set the local preference on the primary link, as well as I'm going to do that on the secondary link. So first, as we mentioned, we have to enter router R2, VTYSH session, configure terminal, and first we have to create the route map. Gonna call it primary N, and gonna give it, the action is going to be permit, so local preference. And basically what I'm doing here is I'm following the same steps as in this lab, as we can see here. I've already skipped all this part because they are already pre-configured. And now I'm here. I'm setting the local preference to 150. Exit. And now what I'm gonna do is that this will be assigned to the neighbor 192.168.12.1, which is basically router R1, and the route map is called primary N, and here is for the inbound network traffic. I missed. Oh, I'm sorry, forgot to. Okay, so now I've assigned the local preference on route on the link between R1 and R2, and similarly, I'm gonna do the same steps on router R3. Route map, secondary, and now we're gonna set the local preference to 125 as we mentioned earlier. 125. And we have to assign it to the neighbor. One and 192.168.13.1 route map, and the route map is called secondary, and we're gonna apply it for the inbound network traffic. So now the link R1 R2 should have a local preference of 150, and that of R1 R3 should have 125, and the preferred route for network 1 is basically going to be this link R1 R2. If we show if we show the BGP table of router R3, I'm going to go back to the topology of the file. Okay, so this is router R1, R3, and to reach the network 192.168.1.0, it's going to use the primary link 12.1 as the next hop. And as we can see here, there are two next hop. The one that's preferred is 12.1, and we can see that from the star, because the arrow sign, because this indicates that this is the best route that the router is going to select. And in case the primary link failed or is like some failure, it's gonna use the secondary link as a backup. So yeah, so that's for the local preference. The MED attribute also can be configured on both routers, so that now router R1 learns how to steer the traffic to the campus network, and to do that, it's the same here also. So this is router R2 terminal. We create a second route map, called it primary med out. The action is permit. The metric for the primary one is going to be 50. And as we mentioned earlier, the lower metric, the lower med is the one that's preferred. Now we're gonna assign it to the neighbor, which is router R1 192.168.12.1 route map primary med out, and this is the name of the primary of the route map, and we're gonna apply it to the outbound network traffic, because basically we're telling the external autonomous system how to steer network traffic to this autonomous system. Similarly, we do the same thing. We set the MED on the secondary link between R1 and R3 on router R3 terminal. Route not secondary. Now this has a higher value because that's not preferred. That's not the preferred one. And the neighbor is 192.168.13.1. This is neighbor R1 route map. And now basically when we set the MED attribute, we're affecting other autonomous system. So now when router R1 needs to steer the traffic to the campus network, it should select the primary link. And we can validate that by showing the BGP table of router R1. So basically, in order to reach the network 192.168.3.0, which is this one, 192.168.3.0, it's going to use the primary link as the preferred one, which is 192.168.12.2. So yeah, in conclusion, this attribute can be used to steer network traffic, because basically the default behavior of BGP is to it counts on the number of hops. So regardless that here to reach router R3 from router R1, it can have like one hop, but using this attribute, we were able to steer the network traffic to use the primary link and like deliver the packets. Yeah, and that's it about for lab 8. Other labs that are also covered include next hop, full mesh BGP, route reflection in order to solve the problems of full mesh topology. We have multi-protocol BGP and other security-related BGP sessions. So that's it, and thank you.
Let me see. Thank you, Ali. I'm sharing my screen. You went through a lot of information. I'm not as sharp as you are, but I just want to remind the audience that what Ali was covering in few minutes was quite a bit iBGP, eBGP, local preference, MET. It is described in detail, step by step, in the lab manual, and the same applies for other labs. Now we have a break right now, 2:30 to 2:45. The plan is to continue discussing about BGP labs. Ali will continue with the second session. He will be talking about BGP hijacking and some ways to mitigate BGP hijacking. So we'll have a 15-minute break and we will be back at 2:45 p.m. Eastern time.